Okay, this is a video based on this book called Vector Calculus, and the author is Susan Colley. And we're only going to talk about part of chapter 1, so there's many other chapters, but we're not going to cover that. So we're just going to go through this quickly, but hopefully it will make things clearer for what we need to do. So they talk about what do we mean by a vector, and a vector is just here in this definition, it's just an ordered pair of real numbers. So just an ordered pair of numbers, for example, this could obviously also be called a point, but it can be a notation for a vector. And then we can also talk about an ordered triple. For example, here, these are kind of strange numbers, but there's three numbers there, pi, e, and the square root of 2. Those are just three numbers, and so this is called an ordered triple, and this could also be a vector. And when we only have two elements, we say that the vector is in R2, and if we have three elements, like this one, we say the vector is in R3. And in this book, they say that when they want to indicate a vector, they're going to use a bold-faced letter like this A, and it won't be capital, it will be a small letter. So if someone is trying to do this on the board, on a chalkboard or on a whiteboard, then it's kind of hard to make a bold-faced. So then sometimes they put an arrow like this instead of making it bold. But since you can easily make something bold in a book, they're going to use the bold face for a vector. And here we just mean that instead of saying what specific numbers are, we just call them A1 and A2. And same thing here, A1, A2, A3. And then they say as opposed to something like a vector, you might just have something like this. Notice this is not bold. So that would just stand for just a single number, which is also called a single real number, or it's also called a scalar. So we have vectors versus scalars here. Scalar is just a single number, not a pair of numbers or three numbers, but just a single number. So we want to be clear, and one thing we want to be clear about is when are two vectors equal? So you might ask, well, suppose you have suppose each of these are vectors, you might say, are they equal? Because you know that if you have sets, if we have two sets, we will call these two sets equal, the same sets. We don't worry about the order that we write them in. So you might think that maybe that's the same thing here, but it's not. These are not called equal. So we want to be clear about what we mean by equal when two vectors are equal. So here we say A is one vector and B is another vector. If they're equal, that means that A1 has to equal B1 and A2 has to equal B2. So that's what they say here. A1 has to equal B1 and A2 has to equal B2. And the same thing if you have what we call a three-dimensional vector, a triple, then, and this one, if they're equal, then A1 has to equal B1, A2 has to equal B2, and so on. So, for example, C here, 1, 2, 3, and D, 3, 2, 3, 1, are not equal. Next thing we need to do is say we want to say, what do we mean when we add two vectors? So suppose we have this vector here, and this vector here, and they're both in R3, we call this R3. Then what do we mean by A plus B? So we want to give a meaning to that. And the meaning is that we just take A1 plus B1, A2 plus B2, A3 plus B3, and we do this. So when we add these two vectors, we get this, which is also a triple, or also in R3. And so that's what we mean by A plus B. So with that definition of the sum of two vectors, we can easily see that A plus B is the same as B plus A, because it just means that when you take this one, this one here, that's A plus B, and if you had B plus A, what would you have? You'd have B1 plus A1 here, you have B2 plus A2 here, and so on. That's obviously going to be the same thing, because A1 plus B1 is the same thing as B1 plus A1, and so on. So we can say that this is true. A plus B is equal to B plus A for any two vectors in R3. That's called commutativity. And also A plus B plus C is the same thing as A plus B plus C, like that. That's also true. And then we also did, we want to say what we mean by the zero vector. The zero vector. The zero vector has a property that if you add it to A, you just get A back again. So you might ask, well, what is the zero vector? And it has to, we're talking about a zero vector in R3, so it has to have three components. So the zero vector, and here they show how to prove these, but the zero vector is just 0, 0, 0. Okay, just a quick reminder about these two symbols, R2 and R3. This is read R2, and this is read R3. And R2 just means the set of all pairs, ordered pairs like this, x1, x2. For example, we could have 9, 4. That's an ordered pair. And R3 just means the set of all ordered triples, x1, x2, x3. So we could have like 4, 5, 9, or something like that. So that's called an ordered triple. And this is just the set of all possible ordered triples, where these can be any real numbers and these can be any real numbers. Okay, the next thing they define is what we mean when we multiply a vector by a number. So, for example, it's kind of, I'm not sure why they use this complicated looking vector, but here's a vector called A, and suppose we want to multiply it by the number or the scalar 7. So what does that mean? It just means that you multiply, what we mean by that is that you multiply each of these by 7. So you multiply 2 by 7, you get 14, 0 by 7, you get 0, and square root of 2 by 7, you get this. And from that definition, there are some properties that we can recognize. For example, if you have k plus L times A, it's the same as like this. You can distribute the A to the K and the L like this. And then K times A plus B, you get this. And you have two scalars multiplied in succession. You can do it like this, or you can reverse the order like that. And these all come, and you can show that these are true based on this definition of what they call scalar multiplication. Okay, now we've defined what we mean by a vector and adding them and when they're equal and multiplying them by numbers and so on. Now they say that instead of thinking of them as like this, we can, which is just a kind of definition of a vector, we can also sort of think of them in geometrically. So for example, this, we could take this vector and we could say, oh, well, it's associated with this point here in the plane. Or we could take this vector and we could say it's associated with some point in three-dimensional space. And then she says here that in physics, they typically give another definition of a vector or description of a vector. They say it's something that has a magnitude and a direction, but that's really not the way we're defining it here. It's not really having a magnitude and a direction. It's more just like a point. A point doesn't really have a magnitude or a direction, but we can also think of it in this way as well. So in other words, instead of taking the point like that, we can think of this arrow. So it's just another way to think about vectors. So one way is to think of it like this. Another way is to think of it like this. So we label this arrow as A. and we label this arrow as A. And then there's one kind of anomaly there, and that is, what about the 0 vector? Does it ever really have magnitude and direction? Well, we might say it has a magnitude of 0, but it doesn't have any direction. So that's a kind of exception, but it doesn't really pose much of a difficulty. And then she says that even though we are thinking basically of vectors as originating from the origin, in physics they don't actually demand that. And we can have, this is a vector, A, we can call it A, but we can sort of move it around, especially in physics they allow you to do that. Basically, that's because we could sort of move around the origin to sort of suit our demands. So if we have a rocket ship that's taking off over here, and it's going to take off in this direction, why not just move the whole coordinate system over to here? So it sort of makes everything simpler. So then we sort of are also equally able to sort of move vectors around. So they say here that A can be moved around all over the place. It's still the same A. It doesn't actually have to be centered at the origin, because usually we can move the origin around, as I said, at our convenience. So if we have this vector here, which we label as A, and if it's at the origin, then its coordinates are like this, then we can take a different one of these vectors, and its coordinates are obviously going to be different. So if we start it at here, and then we have A, then what are the new, and not the coordinates, but the end point is going to be different. So what is the end point for this one? This is going to be x1. This is where we're starting. So it's going to be x1 plus the a1. So that's the new tip. It's going to be here and here and here. So we're just adding the a coordinates. Also, I haven't used that word, but a coordinates to the starting point, and we get this. Now, we already talked about what we mean by adding two vectors, but now that we have a kind of geometric interpretation of what a vector is, we might think about, well, what's the implication of our definition of addition in terms of this geometric picture? So it turns out that if you have a vector A and you want to add B to it, so that's just here, forget about arrows for a minute, just we already said what we mean by this. We explained what we meant. We explained up here what we meant. A plus B means you take the first coordinate, or the first entry of A, which is A sub 1, and you add it to the first entry of B, which is B sub 1. So you get A sub 1 plus B sub 1. And we know how to do this. We know what this means. But what are the implications of this definition visually or geometrically? So we just said, suppose we have an A and a B, but remember that we can place A somewhere, and we can place B somewhere. And remember, we don't have to start them both at the origin. So here, we're not going to start, even though it's the same A, and I mean, we could have this could be our A, and then it could be another B, like over here, or something, or maybe it looks like this, so over here somewhere. But but remember, we're allowed to move the A around, we're allowed to move the B around. So if we allow ourselves to do this, so we put the A and then we move the B like this, and then put the base of the B at the tip of A, and then see where this is. Well, remember, we know what A plus B means. We have a definition for it. It's not a geometric definition, but we know what it means. It just means adding the coordinates. Turns out that the result, when you do that, of adding the coordinates, which we'll give a name, we'll call it A plus B, geometrically, it'll be here in relationship to this A and this B. The new vector, A plus B, will be here, geometrically. So it's kind of like saying that, kind of showing us a method for adding vectors visually. We already have a definition for adding vectors, but maybe we can sort of say what it means visually. Visually, what it means is if you want to add two vectors, you can do this kind of place this one at the tip of this one, and then the result that we're trying to figure out will be the vector which goes from the base of A to where this tip of B would be. So that is A plus B. Now, how do we know that? You have to show it geometrically, or algebraically rather. You have to show, what is it, algebraically or geometrically? We have to show that our definition of A plus B that we have will result in this. And there's also this picture, if you want. This is just another way to visualize what you're going to get when you add A plus B. And here we take A, and we don't put B at the tip. We put it at the same place that A originates from. And so we get something, some shape like this. And then they say construct a parallelogram, which we this shape here. And A plus B will be the thing that connects from here to here. So that is another way of visualizing what our definition of addition of vectors means geometrically. Now, we also already discussed what we mean by this. So a scalar times a vector, which we said here. So if you take a scalar times A, you can just what we mean is that you multiply each of the entries of A by that scalar. So what does that mean geometrically? What is there a relationship between A and the new thing K times A? Is there anything that you might guess about what KA looks like in relationship to A? So that's what they want to see. They want to discuss. Is there some nice visual property that we can notice about what happens when we multiply A by K? What's the result in relationship to the original A? And there is a very nice picture. For example, suppose we have A and we multiply it by 2. What's the new vector? It will be a vector, right? In this definition of scalar multiplication, I start with a vector and I say I'm going to multiply it times some scalar times it. I get this. This is also a vector. So the result is a vector. So what does it look like? For example, suppose I take a vector A and I multiply it by 2. What does the result look like? So here's the answer. Here's A. And if you multiply it by 2, remember what that means is multiplying each of the entries of A by 2. And you do get a new vector. And where is it? Well, it turns out that it's exactly in the same direction that A was, but it's twice as long. So if A went from here to here, then 2A goes from here double the distance to here. So that's a very nice result, that when you multiply by a scalar, you don't change the direction, but you do change the length. Okay, so you double the length here, and then it turns out that if you multiply by a negative, then the length again changes by a factor of 3/2, but the whole direction of A ends up pointing in the opposite direction. So you can check that out with a simple example yourself. Just take some vector like 1, 2 for A, multiply it by 2 and see what you get. Multiply it by negative 3/2 and see what you get. You should sort of be able to show yourself that these properties are more or less true. Okay, so how does the book show this? The same thing. They say suppose you have a vector A and a vector B. So A and B, and we want to know what's the difference between A and B. And they show here visually that it goes from the tip of B, the tip of this one, to the tip of this one, to the tip of A. And we can call it C. So, but the difference between A and B looks like this visually. Now, when we take a point, P1, which can certainly be associated with this vector, but they're just talking about it, so it's a point, not really a vector. So if we take a point P1, which is a vector, but we're just going to say it's a point, and we have another point P2, we call the arrow, which goes from P1 to P2, the displacement vector between P1 to P2. So this is sometimes called the displacement vector. So what does that mean up here? So the displacement vector from B to A is A minus B. So it sounds a little strange. The displacement vector from B to A is A minus B, but that's what we have here. Okay, let's see where this might be useful or interesting. So in this paragraph they say, suppose that we have a particle in space and it starts out at some point. Like, suppose this is the coordinates of where it starts out. And then they say, if the particle moves or travels with constant velocity. So what does that mean? That means the velocity, there is a velocity, but it's not changing. It's the same velocity. So it's like moving at 10 kilometers per second or 10 miles an hour or something, but it's constant. It's not changing its speed. So if it moves at a constant velocity, and suppose it moves for t seconds, so then we would ask, well, where is it now? After t seconds, after 1 second, after 2 seconds, and so on. So if this is where it starts, we can call this a vector. And they call it a position vector, because that's its position. So we can call it A, and A is here. That's the position vector, that's where it starts. And then we can use that word displacement to say the particle's displacement from its original position. So what do we mean by that? Going back to the picture before, displacement vector. So here, suppose it started out here, and then it moved to here. We would call this the displacement vector. So we can ask, well, where will it be after t seconds? So if it's moving, or t units of time, t seconds. So if it's moving at this velocity, it's in 1 second, it's going to be 1 unit of this length away. And if it's 2 seconds, it's going to be twice this far away. So where is it going to be in the end? It's going to be away from A. So it's going to start at A, and then it's going to move away by this amount, depending on the number of seconds. So it's going to start at A, and this is where it's going to be. And this picture looks like this. So it starts here at A, so we can make a vector to point to where it starts at. Anyway, but this is where it starts at, whether you need to draw in this vector or not. This is where it starts, or whether you don't mind drawing in this vector or not. Anyway, this is where it starts. And then it's going to move in the v direction. And then in 1 second, it's going to move v. In 2 seconds, it's going to move twice v. And in general, it's going to move tv. So it starts here, and then it's going to move in this direction. So let's try just the same thing, but just to give it specific numbers here. So instead of saying A, let's say it's here. So let's say a spaceship is here in 3-dimensional space, and it's traveling with a velocity of this. So this means that let's say it's every second, yeah, it's every second, it moves 7, they're calling it miles. So it moves 7 miles in the x direction, and negative 10 miles in the y direction, and 25 miles in the z direction. So it's moving quite fast, right? It's 25 miles in a second. It's huge. So it's moving quite fast. But anyway, suppose that's the way that it's moving. So we would ask, it starts here, where is it later? For example, where is it t seconds later? Or they ask specifically, where is it 20 seconds later? So we just say it starts out at A, so it starts out here, and then it's moving in this direction for 20 seconds. So it's going to start out here at A, and 20 times the velocity, and the sum of this thing plus this thing is going to give us where it is after the 20 seconds, and that turns out to be this. So this is where it is, but also we can ask what's the displacement, and that means how far has it gone and in what direction, and the displacement is 20 times this. And 20 times this is 20 times 7 is 140, 20 times this is minus 200, and 20 times this is 500. So that's the displacement vector. That's the vector that goes from here to wherever it ends up. Okay, I won't go through these other two examples. Here is one more example, and then you can stop the video if you want to and check it. And then here's another example. So I won't go through either of those. And then here are some exercises if you want to do them. Try them out.